evaporation of water. So, there's a lot of things that you have in shrinkage. So, let's look at shrinkage from a microstructural point of view, because we are talking more about microstructure here. You can have drying shrinkage, you can have autogenous shrinkage, you can have carbonation shrinkage, all of those things. Autogenous shrinkage, we talked about it last time, right? When you have a very low water cement ratio cement paste, some of the cement grains react with water because water is available for those grains, but some grains are completely devoid of water, so they start sucking water from the grain that has hydrated, which causes the already hydrated cement grain to lose its volume and shrink, right? So, you create an internal shrinkage, and that shrinkage causes cracking, which I will show how it causes cracking. So, if you look at different time scales, you have plastic shrinkage that happens very early, you have thermal shrinkage and contraction that happens days to weeks, autogenous shrinkage actually happens right all the way here, and then drying shrinkage happens later. Carbonation, I mean, this is not exactly the timeline, but just to show sequentially when this happens. And then you have carbonation shrinkage also. Carbonation shrinkage in areas where you have a lot of CO2 concentration in the atmosphere, where carbon dioxide goes inside, carbonation happens. What does carbonation do? Converts calcium hydroxide to calcium carbonate. The converted volume of calcium carbonate is lower than the original volume of calcium hydroxide, therefore it has to shrink. Okay. Now, shrinkage is a strain. First thing to remember, shrinkage is a change in volume. When I say shrinkage, it is not a stress. Shrinkage is always a strain. The stress happens because of the effect of restraint. Because you are holding on to it and you are not letting this volume change happen. Concrete wants to shrink, but the beam wants to shrink, but you have held the beam in place with the columns, told the beam not to shrink, it has to shrink, it creates internal stresses, right? So, the other very important thing, if you are dealing with any material, stress is a secondary property, strain is a primary property. And you should know that if you plot a stress strain diagram, where do you plot strain? In the x-axis. X-axis is always reserved for the independent quantity, right? And y-axis is for the dependent quantity. Stress is dependent on strain, not the other way. You don't say, well, we say it, I pulled a material with a force of 10 newtons. You cannot pull anything. You cannot push anything. It is your feeling. You have the MTS testing machine guy will come and show you. You can pull the steel rod. You cannot pull the steel rod. All you can do is to apply a deformation to the steel rod. All you can do is to apply a displacement. All the material sees is just strain or displacement. Stress is the superimposed quantity that we put on strain because Hooke came and said there is elasticity. Do you remember what Hooke said in Hooke's law in 1786 or what? He said, as is the strain, so is the force. He did not say as is the force, so is the displacement, right? Ut tensio sic vis is what he wrote in Latin. As is the tension, which is the tensile strain, as is the application of tension, so is the force. So, strain is the independent quantity, stress is a dependent quantity. So, don't tell, when you teach class also, don't ask a question in your exam saying that assume that you are pushing a body with a force of 100 newtons. You cannot push a body with a force of 100 newtons. The 100 newtons is actually imposing a displacement on the body. The body is sitting and saying, oh, somebody is compressing me by 3 millimeters. It does not know what 100 newton is, right? Because if something has to know what 100 newton is, it has to know what acceleration due to gravity is. Which means you are restricting the concept of force to a place where only acceleration of gravity is, right? You see that? What happens if I take it to an outer space where there is no acceleration or no gravity? Is there no force? There is no force. But is there no displacement? You see all these guys in the space suit floating in, no force, but they are getting displaced, right? So, displacement is a fundamental quantity, force is the secondary superimposed quantity, no material ever realizes force, because they see attraction. I told you last class, atoms come together, atoms go away. Attraction, repulsion. Attraction coming close, repulsion going away, pure displacement story. Then we superimpose attractive forces, repulsive forces by multiplying whatever this is by the electronic charge and all of that. Okay? So, if you do that, that becomes much more easier to understand the idea of cracking and stresses. So, there are different mechanisms responsible, but we will do everything from the idea of porosity and pore sizes and surface area of hydration products. So, two things that we have talked extensively on: pore sizes and surface area. Right? We did this extensively yesterday. Size of the pore. Now, why is size of the pore important for shrinkage? Shrinkage is a volume change. Nobody should ever be bothered about just the change in volume, and you should let concrete change its volume if you did not restrain the structure, right? If there is no restraint, no stresses will be developed. If no stresses will be developed, no cracking happens. So, we are not worried about stresses being developed under a free state, but we are worried about stresses being developed under a restrained state. So, now let me ask you a question. What test do you use to measure shrinkage? How do you measure shrinkage? Take a bar, put in 2 studs at the end and measure the length, right? You are just measuring what? Free shrinkage strain. Will that concrete that you are measuring the volume ever crack? If that doesn't crack, why am I bothered about volume change? And is that volume change the right volume change when something is restrained? Again, a wrong test, bad test. Okay? You will get a measure of change in length. Perfect. And you can compare material A and material B and says this shrinks more and this shrinks less. But you don't know anything about the microstructure that might make it crack or not, right? So, the test, yeah, there is a standard, there is a test, you can report the results, you can publish the papers. Overall, waste of time. You should actually do what's called a restrained ring test. Have you seen a restrained ring test? That is the test you should do if you want to know what is the actual impact of the material that you have used in cracking. That tells you time to cracking. That tells you the restrained shrinkage stress that cracks the material. That's a good test. The volume change test is a very easy test. Because it's very easy, a lot of people use it. But restrained ring test is a little more complicated. You have to have strain gauges attached to the ring. You have to put it in a controlled humidity. You have to measure over a period of time. You have to keep looking at when the strain drops and all of that. It's a little more complicated. But what do you say? No pain, no gain. Right? You have quite a bit of work in this, but you will get a lot of useful results. I'll show you some examples. So, if you ever want to quantify these properties, your simple free shrinkage test, it's a nice test to show what shrinkage is. Yes. I did not explicitly mention chemical shrinkage. If you want, we can talk about chemical shrinkage, because in practical aspects, it's not all that important. Chemical shrinkage is basically because the reaction products and the reactants have different volumes. Okay, so the same idea that cement hydrates are 2 times its volume, and that 2 times its volume is not equally contributed to by every component, and therefore there is extra water available along with some components, while some other components are being sucked off water. So you have a differential shrinkage, and that chemical shrinkage. So you really don't talk about chemical shrinkage. It happens very early on, and the system starts to equilibrate very quickly. So a lot of people combine autogenous shrinkage and chemical shrinkage together. And you have you seen that corrugated tube method to measure autogenous shrinkage? People have started selling it now. That kind of measures both together. If you want chemical shrinkage, you can actually do it. You can take a balloon, very thick balloon, put the cement paste in the balloon, seal it nicely, put it in a water bath, and see the mass loss happening underwater. and compare that with the initial stage, and you can do. There are some nice, very simple ways of measuring chemical shrinkage out there if you want to do it. But it is not something that we would really be interested in very common systems. If you put in a lot of nanomaterials, chemical shrinkage. Huh? Through glass jars, yeah. So you can do through glass. You can do glass jars also, but that's more expensive. The way I can buy a balloon, right? So I always try to do cheaper tests. Whatever is cheaper, I can buy. I can go to party shop and buy a bag of 100 balloons, and yeah, 50 of them will have holes in it. But that's fine. $1, I get 100 balloons. I can do so many tests, and people can do in color tests also: green, blue, red. Right? Green is so that's how some of my students do. Green is plain OPC, yellow is fly ash, this is L-curfew. So no confusion. It's all color coded. So very cheap also. It will give you the same thing as a glass jar. Now what is so you have to also see all of these things very carefully. If you buy an isothermal calorimeter from TA Instruments, they'll give you little glass vials to do the testing, right? And they'll charge you an arm and a leg for those glass vials. That's why they make money. So anytime when they say you please measure on this, they are making money. You can buy from cheap places. But they will say, oh, ours is also calibrated. You can't change the calibration, blah, blah, blah. You say yes, 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 and do your own stuff. Many of these things are not that critical. Companies try to make money from you individually. But the glass jar test also is a good test for chemical shrinkage. So, okay. So, and the other thing is that when you get to chemical shrinkage, none of these are there. You have not really formed the hydration products that much. So, volume of surface area is not that relevant. You haven't really have a solid structure, so pore size is not relevant. You are simply looking at volume differences. Reactant volume versus product volume. Okay. Why is shrinkage important? This is just some US information. Transverse cracking in 100,000 plus bridges in the US. Again, since we don't use in the US concrete that much for buildings, and even if concrete cracks in the high-rise buildings, you have glass facade and you have all of this, you won't see cracking. Nobody bothers. Cracking is in pavements and bridges, and pavements and bridges are the biggest consumers of concrete in the US. Infrastructure, and that's where more damage happens, and that's what is exposed to environment and all of that, unless you have a building like an NITK which is totally exposed to environment, right? Otherwise, you have mostly bridges. So early age cracking is very important, because when you have an early age cracking, you are introducing much higher chances for chlorides to go through and corrode, sulfates to go through, all of that. Corrosion, sulfate attack, increased maintenance cost, reduced life. So you can, if you do Life 365, you can account for some of these effects also, maintenance costs and stuff in Life 365. Okay, cracking and warping if shrinkage is not accounted for. So we do a lot of slabs in the US, right? A lot of slabs on grade. Pavements, nothing but slabs on grade. Westergaard equation. Remember your Westergaard equation for slabs on grade? Simple Westergaard equation. Slab on a flat, plate on a flat slab or whatever. So very similar idea. So if you do that, you have a lot of cracking and warping, right? You can have, when temperature changes, cold and day and night, you can have positive and negative curl and warp. You can have a slab curl, slab warp, curl warp, curl warp. What happens if it does so many times? Fatigue, right? Like it's a thermal fatigue. So you will have thermal fatigue and cracking because of thermal fatigue. So you want to control all of that. Contraction joints and pavements and slabs are used to control that. You have to prevent random uncontrolled cracking. So here is a simple picture that you can look at. Cracking happens when stress exceeds the strength. Strength is the capacity to carry load. Stress is the external impulse that comes in. As long as my inherent capacity is more, you will not crack. You don't have to relax. You don't have to relax stresses. Now, cracking is a very natural phenomena that happens under stress. Like people cry under stress, concrete cracks under stress. Very easy. See, even the terms are also very similar. Right? People cry under stress, concrete cracks under stress. So when you have stress and you can't take that stress, there has to be some mechanism to relieve the stress, like people cry. Your crying is, if you ask a psychologist, he'll tell you crying is a very good thing for you. You should cry once every week apparently. That's what they say. We don't have to create a reason to cry. But they say crying is one of the very good ways in which you relax stresses. And we have a lot of pent up stresses that we don't know, so cry. Very similarly, if you have a lot of pent up stresses in concrete, at some point of time it can't take it. So it's a natural mechanism of stress relaxation. It's a natural mechanism by which concrete says too much, relax, right? So it's a natural process. So, like somebody said, Shakespeare said, roses are to smell. So similarly, somebody said concrete is to crack. Okay? So like roses are to smell, concrete is to crack. So it's a very natural process. So the point is, don't try to control every cracking in concrete. And we see that all the time. How do I control cracking in concrete? You don't have to control all the cracking in concrete. It's a natural reaction. Let it crack a little. Sometimes cracking a little is actually good. And cracking a little early sometimes is actually good because it can self-heal. But you should know how much of cracking you can afford to. Not all and then what are joints? Basically predefined cracks. You're telling the concrete, I don't want you to crack anywhere here, just relax your stresses here, right? Cracks are nothing, joints are nothing but predefined cracks. So if you are designing a flat slab, you have to have a way in which you have, because flat slabs, there's a lot of water that is escaping through evaporation as compared to a column or a beam. The surface area to volume ratio in a slab is very high. If the surface area to volume ratio is very high, water has a higher tendency to bleed because there's so much of area available for water to go. When more water goes off, concrete shrinks. It cracks. Whereas so you don't have to adopt the same mechanisms, and you will see here, shrinkage reducing admixtures being sold by companies for beams and columns. Unbelievable. If you have to put a shrinkage reducing admixture in a beam and a column, it means that the designer has no confidence in his design, the concrete guy has no confidence in his concrete, the ready mix supplier has no confidence in what is supplied, everybody is lacking in confidence. You don't need a shrinkage reducing admixture for a beam and a column. A shrinkage reducing admixture is for a slab when the surface area to volume ratio is very high. Is the idea clear? So when again, I have plotted multiple lines to show that nothing in concrete is certain, so that you have a band, everything is a statistical probability. So you have a strength, you have a stress. Whenever the stress exceeds a strength in this region, you can have cracking, age of cracking. Your restrained ring test will tell you what that is. Now, if water loss is what is causing cracking, once I see the crack, I can go pour a lot of water on concrete and reverse cracking? Kind of, right? It's not completely true. There is a little amount of reversible shrinkage. I'll try to get into the theory of this. It might be a little more complicated than you want to, but I'll try to explain that. There is some shrinkage that is reversible and a lot of shrinkage that is irreversible. So water goes out, the pore collapses, shrinks, you add water, you are not getting water back into the pore for it to expand, you are not dealing with balloons here to fill air and take out air. Okay? These are solid structures that have collapsed around. Even at micrometer scale, that water is not going to fill back in. Okay? So you really won't recover a lot of shrinkage. Okay. So remember I told you in the last class about 11% relative humidity story, right? You depress the relative humidity down to 11%, that is when you can say your concrete is dry. So basically if you go and right in front of the auditorium here, the concrete slab, if you go and take the concrete slab there, right up to whatever is the midpoint of that slab and measure the relative humidity, you will have 95 to 100% relative humidity in that concrete. Okay? Even in a dry Mangalore season, if all the rains are gone and the sun shines for 2 more months and no more rain, if you go there, your relative humidity there will be 60%, 70%. Okay? So you will not get to, so escaping of water, especially from the really small pores, is very, very difficult. Right? We saw that, right? Pressure is inversely proportional to size of the pore. Therefore, the really small pore, to eject water, you need a very high pressure or a very high stress or a very high temperature. So you will still have a very high relative humidity. So if you have that kind of relative humidity, therefore it's very unlikely that these slabs will crack. Now, there will be some beautiful contractors who can make it crack, but it's very unlikely that if you're reasonable, it's very unlikely those concretes will crack, provided you give them reasonable joints. Okay, I'm not saying that you can put in a slab 5 kilometers long and it won't crack. No, you have to put in reasonable joints at reasonable spacings. It's very unlikely to crack because of shrinkage. It might crack because of overloading. It might crack because somebody dropped a steel ball on it. Yeah, you can't help that. But shrinkage cracking, it's unlikely because the humidity is always kept high. You see that? Very high humidity. Now, compared to the place that I come from in Phoenix, Arizona, in summer, which is now June, July, there are absolutely no rains. August rains start. In summer, my relative humidity there is 15%, 10 to 15%. The concrete is bone dry. The concrete in the pavements, concrete in bridges are bone dry. Right? 11% is the relative humidity that I said you can take almost all water off. Really, really dry. But again, ambient relative humidity is 15% does not mean concrete relative humidity is 15%. I think there are two different things. Concrete will have a much higher relative humidity, but basically what I am saying is, because the ambient relative humidity is much low and the concrete has some relative humidity, there is still mass transport happening during all this summer, right? There is still chances for internal stresses and cracking all this time. Whereas these pavements or these parking lots and these slabs should never crack. So if you look at what happens, I'll give you what is 1, 2, 3, 4 and 5 are as we go further. Stage 1, you have a little bit of weight loss where at RH change from 100 to 95. And then you have this long stage, these are called Roper's curves, this long stage until about an RH of 50, 45 or whatever, where you have a consistent loss in mass and shrinkage strains. See that? And then around that 10% mark, you are really getting to a point of that 10, 11% relative humidity where things are very, very dry. And then you can get to about this point by just leaving it in ambient at a low relative humidity without doing anything else. For a long time, if you don't do anything else and don't give any additional water, from here to here will take around 25 years, 20, 25 years for a slab. Beyond that, you have to heat. You can't get to a 0% relative humidity without heating. Then you heat, and then at about 105 degrees Celsius, you get 0% RH. When I say 0% RH, it's the water in the capillaries basically. I'm not considering the gel pores here. Gel shrinkage is a different story. We'll just do capillaries. And then you further heat it down, you get a massive loss of water. So all of you have some idea about this curve now? Okay. You remember this picture? We'll use the same model. So that's why you can use the same models. The water in the capillaries that are here, very large pores. Very little drying takes this water away. I'll give you 2 or 3 scenarios for this, for practical applications. Here water, it'll take water very quickly out of here. Now remember, I told you pressure is inversely proportional to the radius, which means, will I create a lot of stress in my concrete if I take water out of here? No, right? Because the pore is large, therefore the stress is going to be low. Because the stress is going to be low, is my concrete likely to crack when water goes out of a capillary pore? Very unlikely, right? Okay. That's scenario number 1. Capillary pores, so every textbook will tell you, yeah, capillary pores are larger pores, water goes out of a bigger capillary pore, no worries, you won't have that much of shrinkage. But water going out of this capillary pore, now listen very carefully, water going out of this capillary pore means what for these waters around it? You have reduced relative humidity around that location, and what does water always want to do? Equilibrate, right? So while the capillary pore has dried out, and while that by itself has not caused you shrinkage stress, you will have gradual equilibration of water from around the local area, which creates, now what happens if the water starts to equilibrate and move away from there? These layers starts to shrink. So, while capillary pore drying by itself is okay, the consequence of capillary pore drying in an extent